All right, guys, we're back with more of our discussion on digital forensics analysis. And we're going to talk a little bit more about um, how that process works and what kind of evidence analysts are looking for. And we're going to start by I'm going to mention that the proprietary tools to use for this process, there's two major ones for general digital forensics analysis. That's NCASE and FTK, right? FTK is now made by a company called Xtero. NCASE is the name of both the company and the software they produce. And both these tools are functionally very similar. Obviously, there's going to be differences because they're made by two different companies. But you insert an image into this software, and it will give you a whole bunch of information about everything that's found on that drive. There'll be tons and tons of really interesting features and tools within this software that allows you to find all kinds of cool evidence and compiles things nicely for you. There is an open source analysis tool also. It's called Autopsy. I highly recommend, if you're at all interested in this, go out and find a copy. Again, open source, free. Download it, start playing around with it. Google some training tools on how to use it. Take a look at all the really interesting features that these programs have. Again, Autopsy, because it's open source, it's not going to be quite as user-friendly. You're not going to be able to call tech support when you have a problem, things like that. But it has most of the really important features of both the NCASE and FTK programs. And is really, really, download, install Autopsy, check it out. It's really cool. I wanted to talk about two of the features that appear in NCASE, FTK, and Autopsy before we move on. The first one of those is the known file filter. Okay. Now remember how I talked in the previous subsection about hashing, how we take this input, send it through that complicated mathematical process, and get a certain output. And every time we send in that same input, we get the exact same output, right? Well, we can use this, right? So we talked about it before just for verifying that the image we've created is exactly the same as the original. But now, let's go through, and every single file that we find on this drive, we're going to hash every single file and see what the output is, that hashing output. And we're going to compare every single one of those outputs against a known file list, right? And there's two different ways we can use this known file filter. The first is a known file filter alert, right? So let's say I've run a digital forensics lab and I work some cases. Early in my career, I find a case with child porn. I'm going to mark every single image I find for this known file filter alert. Every piece of child porn I find, I'm going to say, hey, if you ever see this file again, alert me. And now my software, whether it's NCASE or FTK or Autopsy or whatever else, it's going to know about that file. It's going to save the hash output for the ones and zeros that comprise that image or that video or whatever, right? Now, a week later, a month later, a year later, I'm working another case. I put in this an image from this case, and again, this software is going to hash every single file it finds, and it goes through and it hashes a file, and we get this output, and it compares it against that stored known file filter output, and it says, hey, I've got a match here. The hash output for this file in this case matches the hash output that my user told me to be aware of and to alert them about in that previous case. So I'm going to put a giant red exclamation point next to this file and say, hey, user, you told me to be on the lookout for this certain file before. And because it has the exact same hash output as that previous one, I know the ones and zeros that comprise this file are the same. So, hey, check it out. And now as a user, I get this nice, pretty, thing that says, hey, this file is something you've said to be on the lookout for. So I just make one click and it's, oh, yep, this has the exact same child porn image from that previous case. And now I know it's right there. I've been alerted to its presence. I don't have to go searching for it. The software itself has brought it to my attention because I told it to be on the lookout for that file in that previous case, right? The other way we can use the known file filter is with ignoring it, right? And every computer is going to have gazillions of files on it that are completely innocuous. They don't have any kind of evidentiary value. You know, it's going to be the same old boring thing on computer after computer after computer. It's not useful for us in any way. It's just kind of making it more difficult to sort through everything and find the stuff we are interested in. So what we can do is use that same known file filter feature. Let's say that 3 times fast, right? Known file filter feature. And ignore all those files that we know are going to be useless, right? If it's some stupid README file that comes with a piece of software that's, you know, everybody has on their computer, it's not useful for us. We can say, hey, software, anytime you see this file, ignore it. Don't show it to me. Keep it out of the list of files. It'll still be there, but it won't be displayed to the user when they're looking through it, in order to make it easier to find what that user is looking for, right? So it's a way to weed out the stuff that we know is going to be useless. And once again, when we first start our career, when we first start our digital analysis process, there's going to be nothing in the known file filter. But if we take the time in the early cases to say, hey, this is a file I want to get alerted to again if I see it again, so I'm going to add it to the known file filter alert. Hey, this file is completely useless. I don't need it on this machine. I'm not going to need it in any future case, so I'm going to add it to the known file filter under ignore. The more we take use of this tool, the more future cases will become easier and easier and easier and easier by both alerting us to the stuff that we want to see while also ignoring the stuff that we don't want to see. That's boring, right? So this known file filter, incredibly useful tool, and gets more and more useful as kind of time goes on. The other thing that we can use these software for is for file carving. And file carving is essentially the process I was talking about in the last subsection, where we're going to look for deleted files or even just parts of files, right? And every file type has a different beginning and ending, right? It's called the header and the footer. In other words, this is, the header says this is where the file begins and this is the type of file it is. And then the footer says this is where the file ends and this is the kind of file it is, right? So each different type of file is going to have a different form of header and footer, but everybody's going to have one. So basically, if we want to look for all the JPEG image files, right? Every .jpg is going to begin with the same header that says, hey, I'm the beginning of a .jpg file, right? And that header, as we can see in this graphic here, is FFD8FFE0. And this is just a way of representing binary data in a little more digestible format. But if we go through all these different, again, these are ones and zeros in a more digestible way. If we look at every single 1 and 0 on this drive, anytime we see the series FFD8FFE0, we know, hey, this is the beginning of a JPEG file. I need to interpret all the 1s and 0s after this until I see the footer as being a piece of this .jpg file, right? And if we know what the headers and footers are for every file type, we can now kind of carve out even a piece of that file. So let's say the second half of our JPEG gets overwritten and deleted, but we still have the header. So it still says, hey, this is the beginning of a JPEG file, and we can follow it until we find the header of the file that overwrote that second half. And we can instruct our software to interpret this as a full JPEG file and kind of insert the footer of the JPEG file right before the header of the file that overwrote the second half. And now we've carved out this piece of that JPEG file, and that might be enough to tell us what it was and whether it was legal or illegal, give us whatever evidence we might need to get from it. But that process is called file carving, okay? Now, there are three kinds of evidence we're looking for in any analysis. There's deleted evidence, and we've already talked about this. That was the last subsection, how we find deleted evidence, how we recover deleted evidence. But if we want to delete evidence, if we want to get rid of it permanently, let's say you, as a normal end user, you're wanting to sell your computer, give it to somebody else, even throwing it in the trash, but you want to make sure that all the sensitive information that you store on that device, credit card numbers, old emails, all that stuff, we want to make sure that's gone. Well, there's three ways to permanently delete data, one of which we've already talked about, the wiping process. You can download and install a program that will go through your hard drive and overwrite every single 1 and 0 with just 0, 0, 0, 0, 0, 0, 0, 0. And then usually they go back in and do like 1, 1, 1, 1, 1, 1, 1, 1, and do that a few times just to make sure that they get everything erased, right? So wiping is one of the three ways to permanently delete data. The second is physical destruction of the drive. Send it through a wood chipper, hit it with a hammer, throw it in a lake, put it in an incinerator, right? You physically destroy that drive, all the 1s and 0s are gone. The third way is with a magnet. If you have a sufficiently strong magnet and put it close enough to that drive, it will destroy all the 1s and 0s. This is why you need to be careful. Now, a kitchen magnet, like for a refrigerator on the outside of your computer's case, is probably not strong enough to wipe any data, but at the same time, I wouldn't risk it. Don't put any refrigerator magnets on the outside of your computer. Again, it's probably not strong enough, but you don't want to risk it. But if you got like a really powerful electromagnet and brought it close enough to your drive, that will permanently wipe all of the 1s and 0s without having to go through either the wiping process or the physical destruction of the drive process. So if you don't want to delete data, be very careful with magnets. If you do want to delete data, make sure you're using a strong enough magnet. But outside of those three ways, it's really difficult to delete digital data. And it's even more difficult if you don't have physical control of the drive. So if you're storing your data in the cloud, you don't have physical access to that drive, and thus it can be impossible for you to completely destroy that information. But anyway, when we're doing our analysis, we're looking for deleted evidence, which we've already talked about. We're also looking for forgotten evidence. Things that the user just kind of didn't know was being stored or forgot to delete, forgot to overwrite, that kind of thing. And there's a few different kinds of this forgotten evidence. I'm choosing here to talk about three common ones, but there are more. So first we have temp files, right? So remember, if I open up, say, Microsoft Word, and I start typing a document, all of those 1s and 0s are only stored in RAM, in memory, until I hit that file save button, right? So if I'm typing away and I'm writing my paper and I'm 10 pages in, and then all of a sudden lightning strikes and my power goes out, if I didn't hit file save, all those 1s and 0s are now gone because they were only stored in that volatile memory. Because of this, because there were so many people that lost so much work when they had, power loss or their laptop ran out of battery or whatever, programs like Microsoft Word and lots of others started creating these temp files. And with a temp file, basically, it's like an autosave feature. And every 30 seconds or every minute or whatever the program is set to do, it creates this auto-saved temp file. So now I'm writing away, I write 10 pages, and then boom, lightning strike, power goes out. Once power comes back on, I can turn on my computer and Microsoft Word helpfully says, hey, you were working on this paper and you didn't save it, and then the computer shut down, but I have this temp file stored on the hard drive that I can now restore all that work you were working on because you didn't hit save in a while. And I might have lost, again, 30 seconds or a minute worth of work, but that's a heck of a lot better than losing an hour or 2 hours worth of work. So I'm going to be able to bring all that information back up because the program had automatically saved onto the hard drive every X number of seconds or minutes, right? Now, if I'm writing, say, a ransom note for a kidnapping, and I bring up Microsoft Word and I write out my ransom note and I send it off to the recipient, and then either I never save it or I do save it, but I remember to wipe that original file, maybe I forget to go in and look at the temp files that Microsoft Word helpfully saved for me. Now, when I didn't need the temp file anymore, Microsoft Word automatically deleted that temp file, but again, deleted doesn't mean gone. Think about that previous subsection. Just because it was automatically deleted by Microsoft Word doesn't mean we can't still find it. So even though the bad guy either never saved their work or saved it but then overwrote where they saved it, we might still be able to find this temp file that the program helpfully auto-saved for the user. And now it's not helping the user in this hypothetical situation, but it's definitely helping us as the digital forensics analyst, right? Another kind of forgotten evidence we're looking at is cache files. Basically, what a cache file is, every time you visit a website with your web browser, it saves some of that information so that the second time or the third time or the fourth time you visit that website, it doesn't have to download from the website itself every piece of information. It only has to download the new pieces of information, right? So the first time I go to a website, I have to download everything. But my computer helpfully stores all that information, or at least some of that information, on my computer, so that the second time I go to that website, I don't have to re-download everything. I only have to re-download anything that's changed between the first time and the second time I visited that website. All that other stuff I can just bring up from my cache file. And this can be a good way to tell what websites a person was visiting and when, which can be really valuable evidence that a lot of bad guys forget to delete or overwrite when they're trying to hide what they've been doing. And the third one there, this is not such a common thing anymore, but it's still possible to find swap files. And a swap file is essentially extra RAM, right? So remember, we still have RAM because the RAM to CPU discussion process is so much faster and easier than the hard drive to CPU discussion process would be, right? That's why we still have RAM. We still use this memory middleman because it's able to run programs much faster than if we didn't have it and we had to rely on the hard drive to discuss things with the CPU. So, but what if we have, say, 8 gigabytes of RAM in our machine, but the user wants to run 9 gigabytes worth of programs at the same time? Well, we can't fit 9 gigabytes worth of ones and zeros into 8 gigabytes worth of space. So theoretically, the computer could say, hey, you can't do that. You can't run that many programs at once. But we want our computers to be user-friendly. So instead, what happens in that situation is that your computer will say, okay, the 8 gigabytes that really requires this fast discussion process of RAM to CPU, we're going to save those 8 gigabytes in the RAM, but then we're going to use 1 gigabyte worth of hard drive space as kind of the overflow. And the 1 gigabyte worth of information that the user wants to have in RAM but can't fit, we're going to kind of create this swap file on the hard drive and use that as kind of temporary substitute RAM. And it's not going to be nearly as fast, nearly as user-friendly as that RAM to CPU process because it's on a physical hard drive rather than in that RAM chip. But it is going to be at least possible. And we'd rather have slow but possible over, can't physically happen at all just because you don't have enough RAM space. So if we look on somebody's hard drive, we might be able to find, if we find this swap file, it's like finding a permanently stored chunk of the memory that user had. And of course, it's not going to be all of it. It's going to be nowhere near all of what they had in memory, but it's at least going to be something. And we might be able to find something useful within that file. All right, so we've talked about deleted evidence. We've talked about forgotten evidence. Now, the third kind of evidence we're looking for is hidden evidence. And this is evidence that the bad guy has on their drive and they know that they don't want anybody to see it, so they hide it somehow. The most obvious way to hide something is to encrypt it. And we're going to talk in a future section all about encryption. But encryption, in its short version, is just you take the ones and zeros that comprise that file and you mix them up and scramble them in a certain way to the point where nobody else knows what the heck those ones and zeros are really saying until we decrypt it and put it back into the original order. But in order to do that, we need the key. In essence, we need the password, right? And while that file is still encrypted, we have no idea what it is. We can't tell whether it's a child porn picture or a diary entry or whatever. We have no idea what it is until we can decrypt it. And if we don't have the key, it can be very, very difficult or impossible, depending on the process of encryption, to decrypt it without that key. Now, this is usually, and in many situations, a very good way to hide evidence. Because if you have a really good encryption program, it can be essentially impossible to decrypt that information without the key. But there are a few downsides to encrypted data too. Number one, it's a huge red flag. As soon as we put an image into our digital forensic software, that software is going to say, hey, there's encrypted data, right? It's really obviously encrypted data. So it sends up this big like, hey, I'm encrypted data. Look at me. I'm right here. I'm encrypted. Hi. So it's not necessarily hidden in the fact that it's really obvious that there is some encrypted file there, right? The second problem is a lot of encryption algorithms have some kind of flaw. So especially the older ones, there's some process by which we can decrypt that data without having the key. And then the third problem is a lot of times it's not that difficult to figure out what the password, what the key is, right? Either because you were stupid and you used your dog's name, or, the police say, give us the encryption password or you're going to prison for a long time, or, there's some legal method that a judge can kind of force you legally to give up the password. So if they are able to obtain the password, and again, we'll talk more about how to gain and crack passwords in a future section. But if they are able to gain the password, the encryption really hasn't done anything for you. And it was real obvious for them to find that encrypted file. So there are some downsides to encrypting data, and it's not always the best way to hide data. Another common thing is hiding in plain sight. And this is where you change the file extension, right? So, if I download the latest Taylor Swift music video, but my parents, it's a family computer, I'm saving this Taylor Swift music video. My parents really don't like her music, and they'd get really mad at me if they found that on the drive. What I can do is hide it in plain sight by changing the file extension, right? So when I first downloaded, it might be Taylor Swift .avi. And a .avi is a certain kind of movie file format, right? But what I can do is save it kind of in an out-of-the-way folder and rename it from Taylor Swift.avi to system44.dll. And now, any user scrolling through the list of files in that obscure folder is going to see just, one of those files that every computer has, and we don't really know what they do, but they're required for the system to work, so we don't mess with them, right? It's going to look like any one of 100 or 1,000 other files on that machine that are supposed to be there. But now, when my parents go out to dinner or whatever, I want to watch my Taylor Swift music video, I just have to go back to where I saved it, change the name once again back to, Taylor Swift.avi, watch the music video, sing along with Cruel Summer or whatever. And then when I'm done, I can change the file name back to system44.dll or whatever. And now any other user glancing through the list of files isn't going to see that that's my Taylor Swift music video. They're going to think it's just some innocuous file. Now, remember what I said a little earlier. Every file type has its own header and footer. Thus, when if that computer is then put through digital forensic software, the The digital forensic software is going to say, hey, this file is listed as a .dll, but the header of the file clearly indicates that it's a .avi. Maybe my user should know about this. Hey, user, this file has the wrong file extension listed. So hiding in plain sight might hide that file from other kind of regular users, but digital forensic software is going to find it really easily and bring it to the attention of the analyst very quickly. Okay? Now, the third type of hidden evidence I want to talk about is steganographic data. And this is the one of the last things we're going to be talking about in this section, but this is one of my favorite. For one thing, it's got a really cool name, right? Steganographic. That's a fancy word. I really like saying it, right? And steganographic data is just hiding data within other data. And there's a couple of different ways to think about this. Here's one example of a really simplistic way to hide data within other data. So many years ago, there was a government shutdown here in the United States. And federal government employees were told kind of, don't come to work, you're not getting paid, don't do your jobs, like the government doesn't have any money to function. But if you are a required personnel, if your job is super important that we continue to do it, you have to keep coming to work and doing your job, but you're still not getting paid. And one job that fell under that umbrella was the weather service. And each kind of station for the weather service has to put out either daily or even, more than daily reports of what the weather is looking like in that specific geographic area. So in Anchorage, Alaska, during that government shutdown, when the people who were working there were still working but not getting paid for it because the government was shut down, they put out this report. And at first glance, it looks like any other kind of weather report. Pressures at the center of the western Gulf surface, low, continue, level is dynamic support, blah, 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 right? Looks like a boring old weather report. But if we look at the first letter of each line, there's a hidden message. If you read it down here, it says, please pay us, right? So again, this is a very simplistic way to hide one piece of data within a larger piece of data. Another way to do this, a little bit more complicated, but still relatively simplistic, is by using images and the least significant bit. Okay? So basically, if you zoom in really close on any given digital image, whether it's a frame from this video or any, JPEG or PNG that you download from a website, whatever, if you zoom in really, really, really close, you're going to see that picture is just a collection of square dots like this, and each dot is one solid color, right? So here, again, a simplistic example. We have this image. It's 4 pixels. Each pixel is one solid color, in this case, kind of red, black, yellow, and blue, right? The ones and zeros that are actually storing this information, right? We have to have a set of ones and zeros that tells this pixel it needs to be not only red, but this particular shade of red. The ones and zeros that make up that color code look like this. It's 8 ones, 8 zeros, and 8 more zeros. Anytime an image has this sequence of ones and zeros, it knows that the color it's supposed to display for this pixel is this shade of red. And if we change the numbers here on the right side of these ones and zeros, that's going to change the color of this red. It's going to change the shade of this red, but by a teeny tiny amount. It's going to change it. Like if we change this 1 to a 0 here on the far right, if we change that 1 to a 0, it's going to change the shade of red here, but it's going to change it in such a tiny way that the human eye is incapable of distinguishing it, right? Now, if we change this one here on the left to a 0, because, again, we read from left to right, and so do computers read kind of from left to right. If we change the ones or zeros on the left, either from a 1 to a 0 or from a 0 to a 1, it would change the color of this pixel a lot. But over here on the right, because those are read later in the process, changing these 1 to a 0 or this 0 to a 1 or whatever is going to change the shade a teeny tiny, tiny amount, right? So now we've got these 4 pixels. Each one has its own unique color code that gives it this particular color and tells the computer to display this particular shade of red and yellow and blue and black. But now let's go through and let's change the last digit or 2 to whatever we want. So we're going to kind of hijack these last 2 numbers for all these different bytes of data dictating what color these pixels are. And we're going to change this 1, 1 from up here to a 0, 1. I'm going to change this 0, 0 to a 1, 0, right? And change this 1, 1 to a 0, 0, and change this 1, 1 to a 0, right? So now we have modified the colors from this original shade of red and yellow and blue and black to now this slightly different shade of red and yellow and blue and black. But again, since we only changed these numbers on the right, way over here at the end, the difference in color between this red and this red, or this yellow and this yellow, is so subtle, so slight. I can't tell the difference. Can you? Right? So we subtly change the color of each one of these 4 pixels. And in the process, we've hidden these, 2 bits of data per 1 byte of image data. And now we've hidden 0, 1, 1, 0, 0, 0, 0, 0, 0, 1, 0, right? And if we pull those out in sequence, we get these 1s and 0s, which then correspond, if you translate this from binary into English, to C and A and T. So now we've slightly modified this image, and we've hidden this data inside, which in this case is just the 3-letter message, C-A-T. And if we do this on a much larger image, right? So we take this image of a tree, and we start hiding 1s and 0s for a different image at the very end of the digital data for the pixels for this image, we can now take this image and hide this image inside of it. But only the people who know to look at the very last couple of bits on each pixel for this image will be able to recreate this image. Anybody else looking at this image is just going to say, oh, it's a tree. It's a picture of a tree. And unless we specifically know to go looking and specifically how to pull out all the 1s and 0s that comprise this image, we're never even going to know it's there. That's steganography. And that's a really cool process, right? There's evidence that that process has been used by things like terrorist cells to securely communicate different messages from kind of the main terrorist group to random terrorist cells. Now, the very last thing we're going to talk about is just reporting, right? We talked a little bit about this in the last section. But when it comes to reporting, there are 3 things I wanted to make sure and emphasize. Number 1, make sure at the end of every case, kind of think to yourself, am I a victim of confirmation bias? In other words, am I only seeing what I want to see? When this case started, did I kind of have an idea in my head of what was going on here and did I ignore everything that pointed at something else, right? You need to ask yourself, am I only looking at what I want to be there? Or did I actually see what was there? Even if it didn't kind of conform to this idea in my head of what the evidence was going to show, right? So we have to be careful of confirmation bias. We have to kind of mark and put into our report every piece of evidence we can find, whether that kind of conforms with what we want it to say, or whether it maybe points towards something else happening, right? We need to make sure that we include all of that in our final report. The good news is most digital forensic software has built-in reporting tools. So all we have to do if we find, say, a piece of child porn, we just have to kind of right-click it, say add to report, add to bookmarks, and then we can go in at the end and look at, all of the different things we've bookmarked, all the different pieces of evidence we found. We can label them. They get automatically labeled with where on the drive they were, when they were saved on the drive, when they were found by the analyst, all this different information about each piece of evidence gets automatically generated. All of those different pieces of evidence are then compiled into one giant report, and now we can hand it to the prosecutor, and they have a much easier time going through it, figuring out what all the evidence is, how it was found, when it was found, how it ties together, all those things. Makes creating that report so much easier. And then finally, I want to end with just one more time talking about how difficult testimony can be. Once you've created your report, send it off to the prosecutor. That's not the end of the case, right? Maybe months later, maybe years later, you might have to go in and testify if that case goes to trial. And at that point, you have to, remember what you did. And it could have been months or years after you actually did it. So you have to keep good notes. You have to reread your reports. You have to kind of remind yourself about this case before you go up to testify. And then when you do testify, you have to be able to explain all these things you found, from the hashing process, the imaging process, how and why you found deleted data, how you found steganographic data hidden within this image or whatever. You have to be able to explain that whole process to a jury of 12 people who have no clue what you're talking about. You have to be able to explain it simplistically, but accurately, so that you're not perjuring yourself while also getting those jurors to understand. And then when the other side's lawyer is examining you, you have to be able to answer their questions and make sure that they're not introducing doubt in a way that they shouldn't be introducing doubt about your work, if that makes sense. Anyway, that's the end of a very long, very technical section. Again, I know this is super complicated. Please feel free to watch this a couple of times. Send me a message if you don't understand, need me to explain something more, something differently. But if you made it this far, I really appreciate you watching. I'm going to go take a break.